Assalamu alaikum, this is Dr. Ali Mugibel. Today's lecture is about multiple random variables. So let's start. We'll look at the following topics. We'll look at the introduction. Then we'll look at vector of random variables. We will consider the joint distribution and its properties. The distribution we mean the CDF. And then we'll look at the density function, the PDF, with its properties. We'll look at conditional distribution and density functions. Then we'll look at statistical independence. And we also will consider the special case of sum of two random variables. And then we'll conclude with the central limit theorem. So let's get started. Vector of random variables. What is vector of random variables? Recall the example where we had the parachute landing, and here is the target, this is the eyeball, and then previously we look at how far we are from the target, because we had only one random variable that represents the distance from the target. Are we close? Are we far? So we define the distance, but we are not sure exactly where we are. Now we can be more specific by defining the x and y coordinates. Given the x and y coordinates for the landing, or the point on space, creates two-dimensional random variable. So the example of describing the impact position as a point in a plane, as opposed to just representing it with a line, is an example of two-dimensional random variable. So we can think of an experiment with a sample space S, and then every small s, every outcome of this experiment is mapped to the two-dimensional space. So we have x and y here. So this point, the random variable y will give you the y coordinate, while the function x will give you the x coordinate. If we locate the points jointly in this space, we have two-dimensional random vector. And of course, we have Sj, which represents the range, or the product space, or the joint sample space, because we are representing things jointly. So we have now an idea about vector of random variables. We can mathematically define it in the following way. A vector of random variables is called random vector, and it's a mapping between the sample space and the real numbers. This is for one random variable x. Similarly for y, we are mapping the outcomes of the experiment to the real numbers. We're giving them numbers. If you do it jointly, so you take a vector of x and y, the height and the weight and the GPA, whatever two things you look at jointly, pressure and temperature, then it's going to be a mapping between the experiment and r squared, or we have the two-dimensional real numbers. So here are individual random variables, and here if you look at things jointly, we have a vector of random variables. Consider the example of tossing a coin, and then looking at tossing a coin 2 times, and then looking at the outcome. We have head, tail, tail, head, or tail, tail. If everything is fair, then the probability of every one of these events is 1/4. That's just an experiment. We can convert this experiment into a single random variable by defining the random variable x, for example, as the number of heads. So the number of heads in the outcome is a random variable. This is an experiment, and now we have a single random variable, and we can now say that operating on the outcome HH will give you 2, HT will give you 1, TH will give you 1, and then TT will give you 0. That's we are just counting the number of heads. Here we have 2 heads. We have just 1 head, and so on and so forth. We can also define another random variable y, which is just indicate the similarity between the two outcomes. So if the two outcomes are similar, then we give it a number 1. If they are not the same, we give it -1. So we can say that y operating on those outcomes will give you 1 if we have head, or 1 if you have tail, tail. Otherwise, you get -1. -1 says or indicate that the two outcomes are not similar. Now, if we are asked about a joint event, the probability that x equal to 2 and y equal to 1, x equal to 2 and y equal to 1, that represents the probability of head-head, which is of course 0.25 or 1/4 of the possible events. We can also say, for example, the probability of the joint x equal to 1 and y equal to 1. In that case, we have the number of cases where we have x equal to 1. I'm representing them with green here, so head, tail, or tail, head. If you look at the intersection, the joint, and where y equal to 1, which is similar, you can see here that we have no intersection, so we're looking at the set phi. So the probability of phi is going to give you 0. There is no case where x equal to 1 and y equal to 1 at the same time, so the probability equals to 0. We can also look at not just equality, we can say what's the probability that x is less than 1 or y equal to or y greater than 0. So I'm keeping the green color for the x. So the case where x is less than 1, we have only one case here, tail. And the case where y is greater than 0, we have two cases here. So the intersection between these two is just one case, which is tail. And that's 1 out of 4 possibilities, which is 0.25. So in this slide, we have seen how to look at joint events. From there, we'll start building our random variable. So we can say now, to generalize, I gave you the example of 2 dimension, but to generalize, in general for z, if we look at a vector from z1 up to z capital N, it's a mapping between the outcome of the experiment and the real numbers. Okay, so we have n-dimensional random vector. We could have 2 dimension. In general, we can have n-dimensional random variable. Looking at the outcomes as a vector, as opposed to looking at individual random variables, this will allow us to study their relation, how these are related. So if we have x and y here, if we look at them individually, we don't know if they are related. But if we look at them as a joint random variable or as a vector of random variables, then we can understand how are they related together. Now we formally define the joint distribution and its properties. We know what distribution is and its properties, but now we look at joint distribution. That's multi-dimensional distribution function. Okay, just recall that we define 2 events. A, the probability that x is less than a given value, and B is the probability that y is less than a given value. So if you consider both of them jointly, probability that A intersection with B, it means we're looking at the probability of both of x and y should be less than a given number. Look at this, for example, look at this curve here. We have x and y. For the event A, then we are considering everything below x. And for the event y, we're considering everything below the vertical axis point y. So we're considering everything here in the intersection region. Now, the joint probability distribution function will satisfy both at the same time, and that's what we call the CDF. In general, if you want to generalize for more than one variable, for more than 2 variables, then we can say that f x1, x2, x3, it's the probability that all the variables are less than a given specific value. So just like we have a CDF for one random variable, now we extended this to 2 or even more, and in the subscript we write the name of the random variable, and here the values that we have. We have, since we defined the joint distribution, we also can define something called the marginal distribution. We'll do this through an example. Let's take this discrete example where we have 3 possibilities. We can have x equal to 1, y equal to 1 with 0.2, x equal to 2, y equal to 1 with 0.3, and finally we have x and y equal to 3 with a probability of 0.5. Now, if somebody says the CDF xy to 1.3, it means that the green x must be less than or equal to 2, and y should be less than or equal to 1.3. Which of these satisfy the condition here jointly? We find that there are 2 scenarios which satisfy the condition, these 2. So then that will include the first two probabilities. We'll add 0.2, 0.3. We cannot add this because this is not in the region of interest. So the total, the CDF equal to 0.5 at x equal to 2 and y equal to 1.3. Now the sketch on the side here shows you the PDF. So it's a representation of the probabilities. This is x and this is y. And these deltas represent the possibilities. We can show this graphically for the values of x less than 2, we are considering this region. So we don't include this. And also for y less than or equal to this value, so we are considering 0.2 and 0.3. The CDF is the sum of the elements here. We can also define the marginal probability. The marginal probability is from the joint probability, we can get the marginal probability. The marginal considers only one random variable. So the other random variable will be marginalized. So for example, I am asking what's the probability of y equal to 1. I'm not caring about x. I'm marginalizing x. I'm just looking at y. So it's going to, we have two scenarios, so it's going to be 0.2, 0.3. I don't care about x, whether it's 1 or 2. So here this is marginal probability because it's only one random variable. So we consider the first two scenarios and we got 0.5. For the case of y equal to 3, okay, remember I'm not looking at x, so I get 0.5. And then for the case of, we can find the marginal with respect to x. So there are three possibilities for x, and these are the associated probabilities. Okay, remember that this case we added the 2 because both of them has y equal to 1. We can sketch the marginal probability and we can show things in the diagram. So now we also look at the joint distribution and its properties. Let's look at the properties. Or we look at properties of the joint distribution. Okay, now the first, these are similar properties to the one-dimensional case. Over here, we have a bit of extension. Recall that the CDF at minus infinity equal to 0. Now the CDF at minus infinity equal to 0. But even if any one of the variables is minus infinity, we still get 0. Because this is saying, what is the probability that x is less than or equal to minus infinity? Or y is less than or equal to minus infinity? We don't have such case, so we get 0. Or even if both of them are minus infinity. Similarly, we can say that the CDF at infinity, both variables will give you 1. And then we know that the CDF has values between 0 and 1. The CDF is always a non-decreasing function. It could flat, it could be the same value, so it's non-decreasing. We don't want to say increasing because non-decreasing does not equal to increasing. It could stay as is. And then we have also the following property. If you want to use the CDF to find the probabilities in a certain range, it was a little bit easy in the case of one dimension because you just subtract f at y2 or f at x2 minus f at capital F at x1. But now we have 4 different terms. The terms with equal with 2, 2 and 1, 1 with the same numbers in the subscript, they have positive sign. And then we have x1, y2 or x2, y1, they have a minus sign for both cases. So we have 4 terms and 2 terms which are similar, we get a positive sign, and the 2 terms we have a minus sign. I'll explain why in the next slide. So just bear with me. And the final property here, if you want to get the marginal CDF, from the joint, all you need to do is to substitute infinity for the other variable. So if you put y equal to infinity, you get f of x. If you put x equal to infinity, you get f of y. You can also generalize if you have multiple random variables, like here we have 4, whatever is be substituted with infinity will be marginalized and I get the remaining variables. So let's focus on how did we get this number 5 property. Before I proceed, we can have the following test, okay, to check whether our PDF or the CDF is valid or not. Because a CDF should always satisfy the following properties, should be non-decreasing, should have 1 at infinity, and so on and so forth. You have these 1, 2, and 5, you can use them as for testing purposes. All right, this is the property number 5. Let's explain it how we got it. If you want to find the probability in the following range, then basically here is the X range and here is the Y range. You're looking at this square. You want to find this probability. So let's take it one term at a time. I want to cover this probability. So if I take the CDF at x2, y2, then what you have covered is everything below here. Of course, this includes even the left and the below region. I'm just not showing them here. Now, we have now the big square. What I want is a small one. So we need to start subtracting. x1, y2, okay, so this is going to subtract this region in the left. So we remain with the following region. How do we get rid of this region? If we subtract the CDF at this region, okay, then this is what we have removed. Now remember here now that we have subtracted this region twice. So what we need to do is to add this again, and this is what this term is doing. So with that, we have 4 different terms: x2, y2, this is positive, x1, y1 is positive, and those two are negative. We have added this term because we have subtracted the square twice. So I think that would make it easier for you to recall. Now, the marginal distribution, here we see the pictures I showed earlier, or the figures, they were for the PDF. Now we're showing, for the same example, I'm showing the CDF. Remember that it starts at 0 and then it peaks at 1, at plus infinity and minus infinity. If somebody asks for the marginal distribution, then we just recall the values for your sake. This is the joint CDF. The joint CDF, because it's discrete, it's made of unit step functions. This is the probability value, and this is the subtracting the X value and the Y value. You should be able to, given these probabilities, you should be able to write the following expression. We have 2 unit step function multiplied by each other because we have 2-dimensional CDF. Now, if you put this infinity, if you want to get the marginal, you substitute for infinity. What's the unit step function at infinity? It's going to be 1. So it's going to just drop. So from here, we can find the marginal distributions. If you put y equal to infinity, this blue term is going to disappear because it's going to be 1 at infinity. And then what remains is the following probability. But you have to be a little bit careful, because now if we do it for the second case, if you want to get rid of y, get rid of x, you substitute infinity here, okay? And then these terms are going to disappear again. Okay, so we got the following expression. But this can be simplified because we have 2 unit step function with the same coefficients, if you like, and then if we add them together, we can say that we have the following CDF. So it would simplify to 0.5 and 0.5. So that's the unit step function that we just received, or we just got. And the PDF and the CDF for the X case is shown here. You can think of this. As if you want the CDF for X, you look from this side, okay, and you get the following curve. But if you look from the other side to get the marginal, you will not observe this. It's just going to look at one step, which is 0.5. So margin, it means you ignore one and you look from the other side. And the following, we'll just conclude this part with some graphical sketch of illustration of some examples for the discrete. We have shown this example earlier, and this is the PDF, this is the CDF, and we have also the marginal distributions. If the joint random variable is not discrete, we get a service. So we have this kind of stairs and deltas in the 2-dimension. If you are dealing with discrete, if you are dealing with continuous random variable, then we have this kind of shape, which is a kind of service. So next we're going to look at the density function in the next few slides.